Welcome to Learning to See the World Through Mathematical Lenses. This course is for students of mathematics, physics, engineering, computer science, and anyone who wants to understand mathematics rather than memorize it. After more than a decade of tutoring and teaching, I've become convinced that much of mathematics is built on just a handful of remarkably powerful ideas. Once you truly understand them, hundreds of formulas compress into a much smaller set of principles. The goal of this course is to help you discover those ideas for yourself. And this idea kind of came to me a couple of months ago, and I just ran with it, and it ended up being a pretty deep exploration. So today's lesson is all about time, accumulation, which is a word that I don't think is mentioned enough in earlier mathematics, and approximation, another word that I think could be mentioned more. So let's start with time, something that we all kind of take for granted. So I want you to imagine that you lived in a world where nothing ever changed. There were no shadows, no sunrises, sunsets, no precession of stars in the night sky, no heartbeats, no animals moving, no waves or tides. And the question is time, would it be meaningful? Would that time be a meaningful concept in a world like this? Kind of one of those questions you ask when you're on LSD.
I mean,
I
isn't
guess
time really a measurement of change itself? I mean, without change, there really isn't the idea of time.
Yeah, that's a good point. Like what is the point of time if not a parameter by which to track change? Does anybody have any opposing views on that?
I think it really depends on like the. I agree with Jonathan, but I think it kind of depends on like if uh if you're talking about like a completely empty world or a completely static world, then where there's like nobody that can observe it or anything like that, then I guess it depends on what do you mean by like if there's a meaningful concept of time, if there's no one there to think about it.
Fair enough. Say you were there and you could move and you could make things move, but everything else just stayed still if it was unperturbed.
I mean, I think it would still have a use in that case, but maybe not as much of a use. Like height, like if for whatever reason you just wanted to know how long ago you moved something,
Right,
or
exactly.
but there there wouldn't be too much like practical application,
Right.
I
So,
suppose.
if nothing around you changed on its own, you could still create a way to track time, right? If only for your own curiosity. Um,
Yeah.
let's
Although it
see
would be
here.
hard if nothing moved on its own to track time.
It would be really
Maybe
difficult, right?
just
And
your internal
so,
clock, I guess.
right, just like Jonathan said, like a useful way to think about time is just a parameter used to compare changing states of a system. So tracking time scale is a big human problem because nature actually gives us the ability to track large time scales pretty much for free, right? The day is such a natural measurement of time. Sunset, sunrise, the phases of the moon give us the month. Other celestial bodies, you can kind of see time scales, longer time scales. Shadows cast by the sun, and even seasons and temperatures get you to the quarter of a year increment. But shorter intervals require a lot more ingenuity to track. But they're still really important, right? Like how long until the food finishes cooking, or how long until the candle burns halfway down. Or just more generally, how can observations be measured to allow short lived events to outlive the moments and locations in which they occurred, right? Even thinking back to like sports, right? Like at some point, people just ran against each other and like they didn't have like a world record. It was just whoever won that year was the fastest on earth, regardless of whether somebody 2 years before had run a faster time, right? It's just, well, person A beat person B and person B beat person C. Therefore, person C is better than person A. And we don't even know what their times were. Um, So humans needed to create their own reference for change on time scales relevant to those kind of phenomena they wanted to observe, whether, it's an apple falling from a tree or whatnot. There's nothing in the sky that really gives us those length of times. It'd be kind of wild to try to use like a sun clock to track minutes. So that leads us to representing time through change, right? Some of the more popular examples in human history were water clocks, sand clocks, candles. I like this candle image, it's got a nice scale on it. Modern examples, the hyperfine transition and cesium-133 atoms used for atomic clocks, as well as the more common resonance of quartz crystals for portable wristwatches. So a question there would be, what makes a process useful as a clock?
They're at regular time intervals, something that um, makes it dependable.
Dependable's nice. Regular time intervals is really nice.
Yeah, I
Taking a
think
look at
a lot
this,
like
like,
short.
oh, go ahead.
I think a lot as well like short time intervals as well, something that you can see move on like a easy to kind of follow along with scale,
Yeah,
I guess.
absolutely. Looking at just this candle idea here, like, do we think that this candle would burn at like a nice uniform rate? Do you think the scale on there is likely accurate?
Maybe over the whole span of the candle itself, but for each individual like tick mark, it could be at different speeds. Plus, it also
Yeah,
depends a lot on the surrounding conditions.
exactly. You bring up a good point. So like maybe it's accurate for a whole candle. Like if you burn two candles made of the same material, the same length, it's roughly the same amount of time, but maybe throughout the process it's not uniform. Like it's not one tick per minute or something like that. So yes, I would agree. At minimum, there has to be a predictable and reproducible pattern, although humans generally prefer steady rates because they could naturally produce evenly spaced tick marks. And then, just for a fun job for Chat GPT, could you imagine having to read a clock like this every day, right? It was so funny in prompting it. It would get the spacings weird, but it'd be like 1, 2, 3, 3, 5, 4, 12, 11. I was like, no, you gotta get the times right still. So like this clock is perfectly useful. It's not as convenient as say a nice evenly spaced clock. Um,
I mean, that's about how I feel a day, you know?
Yeah,
right.
I've
It's like, okay,
really
so
seen the
which I'm thinking of which period is it? Yeah, it's between 4 and 5. You think you have a lot of time to get to work, right? And then,
Hmm.
all right.
I'd love to see the gear mechanism behind that clock to make it
Oh,
accurate.
that'd be a wild gear. So today we're going to focus primarily on the accumulation of fluid in a basin and the relationship between fluid height and fluid volume. Since humans are generally much better at measuring length or approximating length, right? I don't know if anybody's ever tried to look at a pile of gravel and guessed how many cubic feet it is, but usually I'm way further off on a guess like that than I am on, oh, that's 12 feet tall. So for today, we're going to start out with a few simple assumptions, which is constant pressure source, even though we haven't really even talked about what pressure is. But the way I would describe this is if you go to your bathtub and turn the handle to a certain angle and leave it there, it's roughly a constant pressure source with a fixed valve opening. And so the assumption is that that will produce a steady flow of water. So throughout today's session, keep it in the back of your mind. If I had to build a clock from scratch, how might you design it to achieve the steady tick marks? And then starting out, we'll just talk constant fill rate. So once again, our assumptions are that we've got a pressure source that's constant, fixed valve opening, steady flow. So if equal amounts of fluid enter the tub during equal time intervals, what quantity changes steadily?
Is the tub that's entering uniform.
Um, yeah, let's say it's a nice square tub,
Okay.
and it's just we're asking what quantity changes as equal amounts of fluid enter the tub, an
The
I
equal
height
think
time.
of the
like
water.
Yeah,
yeah.
yeah, that seems reasonable, right? And we'll get a little bit more to the height later as well, because like we talked about, humans are better with lengths than volumes. Um, I might say volume, like equal amounts of fluid enter the tub in equal time intervals. So I know for sure the volume's changing steadily, so long as well, with height, there's kind of that caveat of it better be a nice uniform cross section. Um, but then I thought about it and I was like, there's kind of an assumption hiding in my volume as well. So, I assumed volume accumulates steadily, but a steady faucet deposits equal amounts of matter per time. And we often describe the amount of matter using mass, not volume, right? So it's more like mass is increasing. When I say volume increases steadily, I'm assuming that the fluid is nearly incompressible. So, in other words, you can't really squash it under its own weight. Otherwise, the fluid could compress under its own weight and occupy less volume, even with a constant flow rate. And all matter compresses somewhat, but liquids tend to, resist that kind of compression under everyday conditions. Now, this may feel pedantic, but really what I'm trying to do here is this whole course is about building models and recognizing assumptions, right? Because all models have assumptions. And so I want to be upfront about this assumption. I think it's a pretty reasonable one. Most courses wouldn't even mention it. It's that reasonable. But I think it's important that we list out every possible way in which our model could fail. So suppose this faucet's depositing 1 cubic meter per second at a constant volumetric flow rate. What does this rate mean to you? What does 1 meter cube per second mean in your head? What do you visualize?
Be a lot. I feel like just imagine a like a 3 foot by 3 foot cube being thrown
Right.
at you every second.
I was going to say, I chose one because it's a convenient unit, but I was hoping somebody would notice that that's a absurd amount of water for a bathtub.
Yeah.
But, imagine it's zero point 0.1 meter cube per second or zero point zero 0.01 meter cube per second. What does your mind visualize when you see a rate like that?
Consistency, I guess.
What's that?
Like a consistent rate, I guess.
Yeah, so I just gave you one number, so whatever it is, it's consistent.
I would think of like you can figure out however how much liquid it is by multiplying by seconds or anything like that. And it kind of gives you an idea of just how much is going through it. Like in 5 seconds you have 5 cubic meters or whatnot.
Yeah. And that's the beauty of the 1 meter cube per second. Is yeah, you say over 5 seconds, okay. If I get 1 cubic meter per second, then over 5 seconds, I get 5 cubic meters. Personally, I get this picture in my head of a cube of water, length times width times height, because we're so good at squares and cubes and rectangles, right? That our brains just kind of automatically go to that. And then I just imagine that I'm tossing it into the tub every second. And I call that the cube toss model. And the question to that model would be, is it an accurate representation of a constant flow rate? If say I look at my clock and go, okay, 1 second's passed, there goes my next cube. 1 second's passed, there goes my next cube.
I guess, yeah, that 1 cubic meter per second, if you're imagining it as throwing the cubes in, it would be an average over a second. But yeah, it wouldn't be an actual constant depositing.
Yeah, maybe not actual constant depositing. And then just be considering under what conditions the cube toss model would agree with that ideal constant flow rate. So, key ideas, right? We have to get into delta notation early. I feel like one thing that I wish math classes would do earlier is talk delta notation. Is everybody here familiar with delta notation? I know it shows up in chemistry, it shows up in physics, it almost never shows up in math, which is kind of funny. So delta just represents the change in a quantity. And the key idea here is that we might call the change in volume over the change in time, we might call that R for rate, volumetric rate. And in this case, you could think of the delta V as being 1 meter cubed and delta T as being 1 second. So if delta represents the change of a quantity, how do we calculate how a quantity changes over time? Now let's keep it with volume. Let's say I have I don't know, like a vessel shaped like this. And at one point in time, I have this much volume. And then another instant later, or at some time later, I have this much volume. How would I figure out how much volume has accumulated in that time interval?
Compare how much volume was it at its maximum time versus how much it was at the very start.
Exactly. So you may say, like, okay, I measured this much volume at the end of my time interval. I measured this much volume at the beginning of my time interval. And so the difference between the two is going to be the amount the volume has changed in that time interval. So using that kind of logic, really change is measured through differences or subtraction, right? So we've got, and all of you that have seen delta notation, you already know that. Because with delta, you've got, let's see here, delta V, the change in volume, you just take the volume you finished with, subtract the volume you started with, and that's how much you've gained. And same with time. Although time we usually think of as this kind of steadily flowing, just constant basis, you know? And you could also consider that the volume final, there is what I'm using F for, is equal to the volume evaluated at the final time, right? And V initial could be represented as the volume evaluated at the initial time. So, question, if the accumulation rate is delta V over delta T, just as an example, 1 meter cubed per second, and we wait a time interval to delta T, how much volume accumulates?
2 times whatever that change in volume is.
Exactly. So since R must remain constant, right, we've said it's a constant flow rate, then if 2 delta T of time passes, then 2 delta V must pass as well. That way, when we divide the changes, those 2's cancel out and you just end up with R, your rate equals delta V over delta T. And that's what Nick was doing in his head earlier when he said after 5 seconds, I would have 5 cubic meters. So with the cube toss model, you wait, 1 second and you toss in 1 meter cubed, wait another second, toss in a meter cubed, wait another second, toss in a meter cubed. And then with the constant flow rate model, it's really this ratio that works for any number q, right? So if I asked you if I waited 1.5 delta t, how much volume has been accumulated, you would say 1.5 delta v. Doesn't need to be an integer, right? In the case of my cube toss model, I made it an integer. But the key idea is that equivalent ratio triangles sweep out a straight line. So as you scale similar triangles, their endpoint sweeps out a straight line. And that's kind of what this Q delta V over Q delta T represents. We call that linear accumulation because it results in a straight line. So, I feel like we've already answered this, but is the or not this one actually, is the constant fill rate model true to reality? Like assuming, the valves open at the right angle and the pressure's constant. Is the constant fill rate model true to reality?
I'd say it's more true to reality than the cube toss model.
That's fair. And why not
Yeah.
exactly true?
Depends on how pedantic you want to be.
Right.
Yes. Because the universe is discrete, or for the most part, so you have individual water molecules that are having to come out, and of course, small differences in the flow rate that you get with just
Exactly.
variances.
Just fluid
I like
dynamics.
that. I like how confidently you said the universe is discrete. Because yeah, on the atomic scale, it feels that way, but there's still a lot of people that argue for continuity.
But I
But of
followed it was
course,
mostly because I was like, I don't know if I know that for sure.
right. No, it's a hard question. I tend to lean more in the discrete direction myself. But yeah, funny enough, if you shrink down the cube toss model far enough, like Nick said, it's actually closer to reality than the continuous fill rate. We would just need to figure out what what the change in volume of a single water molecule would be and what time interval it would occur over. And on the intervals of which the cube toss model agree with the constant fill rate model is if t initial equals some integer 1, 2, 3, 4, 5 times delta t, and t final equals some integer times delta t as well. So in other words, what I'm saying is, if you waited, say if you waited half of a delta t, then the cube toss model says you don't have any water yet, whereas the constant flow rate says you have a half a delta V. So these two things only agree on their averages on the delta t interval. And I wrote where m and m are integers where m is less than n. What would be the case if, say, m was greater than n, or the accumulation of time reverses?
Would that be like playing it in reverse effectively?
Yeah,
Or okay.
yeah. I think of it like playing the tape backwards. And
Hmm.
honestly, this is kind of one of those things I like to think about because I think humans invented arithmetic to model the world around them. And so when you think about these sorts of rates in terms of arithmetic, if you have a rate of 1 meter cubed per second and you have a time interval of 1 second, then you've accumulated 1 meter cubed. But if you have a time interval of negative 1 second, then you've actually lost 1 meter cubed, right? Because playing the tape backwards, now the tub is draining instead of filling. And so this kind of gives way to like a good naturalistic explanation of why a negative times a positive is a negative, even though we don't really experience negative numbers of objects in our day-to-day life. They really only show up in math. So then you could imagine if you have a fill rate of minus 1 meter cubed per second, forward in time, the tub's draining. So then if you play the tape backwards, it looks like it's filling, right? So this tape game, and for a lot of you that have taken calculus, you've experienced this, and we'll hit it a little bit later, but they say if you flip the bounds of an integral, oop, out comes a negative sign. That's kind of a natural explanation as to why that's the case.
So here it would be like negative is just directional then, right? Like,
Yeah, exactly. Yeah, negative is just up or down. Yeah.
and then like what Nick said earlier, I know I'm kind of going backwards, but like, yeah, the molecules are discrete, but time is continuous. So like, wouldn't it still, I don't know, have the limits of continuity or the rules of it at least, right?
That's a good question. I don't know if time's continuous.
I mean, yeah, I guess you get into like Planck
But it's
constant and
super
everything,
fine, right? It's as fine as our
yeah,
brain can perceive.
yeah.
So what you're saying is if time's continuous, what would be the result?
Yeah, like would we ever be able to have something apply something discrete to it if time is involved?
Hmm.
And then like
I
even
think
if,
how that, sorry,
oh, go ahead.
No, please answer, Nick. I don't have a good answer.
I'm gonna say I think any like uh realistic or like any rate that you're gonna deal with is gonna be averaged over some interval. And so like at least in the real world, if you're doing like strictly mathematical, it might be different, but I think that kind of smooths out any of the like
Mhm.
kind of turns the discrete into kind of a continuous that you can work with. At least like, if you're physically measuring something. But as far as like strictly mathematical, I'm not sure.
Yeah, strictly mathematical is much harder. When it comes to engineering, it's like we're never gonna measure pi. It's just gonna stop at some point, as accurate as our scale is. So it does in applied math, it kind of averages out.
Yeah.
This kind of, I haven't gone fully through this thought yet, but I just want to hear what y'all think about this. But like, let's take, like, if we're measuring a distance traveled over time instead of a volume, where Nick was talking about the discrete packets, like individual atoms flowing into our tub. What if I think about moving a certain distance? Like, are those, would the equivalent of those packets be like a Planck length?
Right.
Like is that the minimum distance that I'm allowed to use? And does that make it a discrete packet of distance?
Yeah, that's a tricky thought as well. Because yeah, I've heard this Planck length is as small as quantum mechanics conceivably goes. So at some point you do wonder if maybe there's discrete chunks there. I do think this is a question worth thinking about. I know that there's some physicists out there, like for example, Stephen Wolfram, who's very interested in a discrete universe, um, comprised of like just a bunch of little cells and data points. I think one reason I've started leaning discrete over the years is because I can't imagine infinite data. Like everything I experience in terms of data has a capacity and the storage capacity. And like if you had continuous time, that's a clock that takes a lot of data to refresh and update.
And there'd be like theoretically infinite data in any small portion of whatever. Although it might not be
Right?
useful data, like it might just be noise. So I don't
True.
know if that changes things.
Yeah, yep. Yeah, so I think those are really interesting questions. I think you'll find that the math works either way, which is really cool. But I think those are good questions to continue thinking about. So far, have I been using delta V and delta T consistently? And if not, explain why.
You did use it to explain a continuous rate, I think, at some point
Right? So I've used it
when,
to describe a continuous rate.
as well as a discrete rate, at
Yeah,
least if I'm remembering.
perfect. So like I've used delta V as like a chunk, like oh, a 1 meter cubed, and delta T is a chunk of time, like 1 second. But I've also used it in terms of like a continuous, like a truly continuous flow rate would be pick any delta V you want, and delta T will match. Likewise, so you can use it over a full interval, or you can use it over discrete chunks. So for a constant fill rate, we can use it over any time interval, right? I've used it in those two separate ways. But luckily, both use cases have worked for the constant fill rate and the linear accumulation because the rate is invariant, right? The rate's the same at every point in time. So it doesn't matter what interval I measure over, I'm always going to get the same rate back, whether I'm using discrete chunks or not. But to answer another question, right, the accumulation rate only tells you how much fluid has been added to the tub in a given time interval. It can't tell you how much water is in the tub. So I want to nix that immediately. Accumulation is not equal to total amount. So let's talk through that a little bit. If you have, say, an accumulated volume to accumulated time graph, and we have some initial time, and at that initial time, we, look at the markings on our tub and see how much volume's in it. Then we wait a certain amount of time and see how much volume is in it at that point in time. Then I could call the change in time delta T. I could call the change in volume delta V. And if I assume the constant pressure and the valves open to an equal angle, then I can interpolate those into this straight line, this linear accumulation rate, which just states that the change in volume is just equal to the flow rate times the change in time. And so you start with some initial velocity, you add some change in velocity, and that always gives you your final velocity. And your change in sorry, I'm saying velocity now, and I mean volume, but we'll get to velocity too. The change in volume is always just equal to the volumetric flow rate times the change in time. So if we want to change this to a total volume function, not a change in volume function, we can just switch our axes up a little bit. And then over what time interval should we run this accumulation rate to find a graph of total volume in the tub as a function of time? What do we think T initial and T final should be set to?
Yes, like T initial, you can, in terms of just like moving our axes to easier.
What's that?
Just like say just setting T initial to 0 and T final to whatever your current time is.
Yeah. So in other words, we've got this change formula, but we're walking in and starting our clock while we're watching the volume accumulate. We may as well set our time axis origin to 0 so that it aligns with our clock. And then the final time, we really want that to be a variable now because we're trying to find a function. We don't want this to be limited to 2 points. So we're going to set our final time equal to a variable. And then we can go ahead and complete the moving of the axes. And what this looks like algebraically is you have this delta V equals R times delta T. You expand out. Where there used to be a T final, you plug in T as a variable. Where there used to be a T initial, we just set that to 0 because that's when our clock started. And then we go ahead and set V final just to be V as a function of T, right? So that it can vary along the curve for whatever time you want to enter in. So now we've got a volume formula as a function of time. So long as we know how much volume was in the tub initially when we started observing, we know the flow rate and how much time has passed, we can calculate for any point in time what the volume will be in the tub. Now, does the size and geometry of the tub change this accumulated volume function of time? Or, even better question, does it change the total volume in the tub as a function of time? So in other words, big tub, little tub, round tub, triangle tub, does it change the accumulated volume as a function of time?
No, the accumulation of volume should be the same, but the size of the tub will change, the height or other properties.
Other properties, yeah. So in other words, the size and geometry of the vessel, say they all start empty, right? it doesn't actually change their volume to time graph because they're all being filled by the same faucet, right? So really, when we were making this model, the tub played no role in the volume time graph. So what was this past derivation really modeling? The R equals delta V over delta T. What were we modeling?
That's more of like a property of the faucet, right? Like
Exactly.
how much the
Right.
faucet's actually dispensing.
Exactly. We were modeling the faucet. We were saying if there was a tub that could hold infinite fluid, right? What would this model look like? Of course, the joke would be that the volume is still accumulating somewhere after overflow, just not your tub, right? It's still coming out of the faucet. Now it's just flooding your house. So yeah, we didn't account for a maximum volume in our model. So with a maximum volume, there's at some point the tub's going to be full, and at that point, if you keep your tub roughly level, right, it'll just kind of level out at its max volume, and it won't allow any more fluid to accumulate. So once again, I think it's so important that we talk about domains of validity of models, right? And this is a pretty straightforward example of that. But as tutors, do y'all find students struggle with this sort of stuff as like domains of validity of a model when they're solving problems?
I definitely see it in chemistry, probably more so than math. Because I think math, the I mean, most of the methods, assuming they're not like special cases, things kind of apply, everywhere. But for chemistry, it's definitely like, and it was a problem for me as a student too, like trying to remember what rules apply in what situations and things like that.
Yeah, yeah, I would agree with that. I think a lot of times in math class and math problem sets, they specifically write the problems to always land within the domain of validity so that students never have to deal with that. They can just grab the formula and plug and chug.
Yeah, I
There
was
is
going to
though
say,
some like,
oh,
go ahead.
I was just going to say this. I think that this is kind of one of the big places where there's a disconnect between the math and the actual applications of it, because the math is kind of in this perfect world situation, and we never really, it's like they're avoiding the true word problem because people are so scared of them.
Yeah, I like to tell people when I'm tutoring physics that math doesn't have a brain. So, it's really good at if you're able to give it its domain of validity and hand it the right information, it can work miracles. But for example, in physics one, when people learn about the laws of motion and how things soar through the air, oftentimes if an object hits the ground, they will just say, "Oh, well, v final must be zero because the object hit the ground, so it must have stopped, right?" And like it feels right in the moment. But the issue is that the kinematic formulas only apply right up until you hit the ground. So the object still has a high velocity before it hits the ground. So I feel like,
Yeah.
go ahead, Nick.
Well, I was gonna say, I think another place I've kind of noticed this in math is remember there's this one problem in like math 143 that you have like a sheet of paper, you cut these corners out of it, and you measure like how big a box you can make with that. And I've had a real hard time trying to get students to think about like, well, what's the maximum, like how tall of a box could you cut? Like how big could those cuts be? Because like, at a certain point you'd start like overlapping your cuts and there'd be nothing, you wouldn't end up
Right.
with a box afterwards. But like when they're so focused on, like just the formulas of it, they miss that aspect. Whereas if you'd hand them a sheet of paper, they would know
Exactly. Right.
intuitively.
Right. It's like, yeah, at some point you cut so far that you have a box made of antimatter paper, right? Or something like that.
I feel like that almost makes it harder in a math class because they go in expecting like I'm gonna get an answer and it's gonna be right. Like if I use this formula, it's gonna be the one answer. But sometimes you have to go back and you have to test it to see if it
Right.
works. Or like with rationals, you have to you can't divide by zero, and so I guess like in a science class, sometimes you're a little bit more prepared for those nuances, but with math, they just expect black and white and not like a gray area.
Yeah, there's like this, like Jonathan said, sometimes it's just nervousness, but other times it's just, oh, this is the formula. Like I'm gonna trust it.
Yeah.
Yeah, that with like extraneous solutions is a big one too, where it's like people go through the
Yes.
thing, they get two answers, and they're okay, those are our two answers, and they're confused why it's wrong. It's like because you're technically skipping a step where you're like being
Right.
like this can't be zero or whatnot.
Yeah, and
This
I
can't
also
be
love
whatever.
I love this idea. I mean, it's true that like right, we try to do the same thing to each side in algebra so that we keep things balanced, right, and we keep an equivalence. But really, every step of algebra that you write is asking a different question, right? It's asking a different question with ideally an equivalent answer. The issue with that is that sometimes it's not perfectly equivalent, right? Like when you divide by x minus 2, you're automatically ruling out that that x could equal 2 by dividing it at all, right? And so yeah, it's tricky because we do like to teach do to one side what you do and to the other formality, but sometimes it sticks so hard that students forget that like each step is its own relationship.
Yeah, I remember that was like kind of a sticking point for me in calculus when we first went over like the limit definition or like the derivative definition and solving derivatives without the actual. They're just like, yeah, just divide out these factors and don't care
Right.
that it'll equals that you're dividing by zero once you actually get to the end.
Yeah, that's a
It's like, but you told
super
me not to do
frustrating
that
part of that. Yeah,
before.
absolutely. Yeah, no, that makes perfect sense. Hopefully some of the exploration we're going to do next will help with some of that limit plug and chug sort of ideology. So now I'd like to just shift, and this is going to be pretty loose and free at this point. I'd like to just start us out with the rectangular basin, which honestly you guys have already answered kind of intuitively. When I first asked what thing would change at a constant rate, you were like, well, is the tub, does it have the same cross section at all heights? And that was a good question. So here, let's say that I want to know the volume function for this particular box filled with some amount of fluid. How would I write that formula?
The volume of the water currently in there or the volume of the whole basin?
Good question, right? Like we may want to start our model and just say there's some maximum that I cannot exceed. So what would the maximum be?
There should be your length times width times height
Yeah,
of your
and
rectangle.
I'm using capital letters for the absolute height and length and width. What about a volume like, you're pouring water in from the top? Which variables change and which stay the same?
The cross-sectional area, so the length and the width would remain the same, but the height is the thing that's changing.
Right. So we've identified like, oh, if they're, if length and width were variable, then that would be a different story, but they're not. Length and width are fixed, and therefore the volume really only depends on the height, right? So you've got length times width times a variable height. Call it little h. Okay, so now let's talk about the geometric change in volume versus the algebraic change. We'll do both methods. Let's say we start with the geometric change in volume. So say I allow the water to fill up through a change in height delta H. How much then would the volume have changed?
It would be that delta H times that length and width.
Yeah. So you got the cross-sectional area, and this time you're just multiplying it by delta H, or the height of that specific chunk of water. All right, so that's the geometric way to approach it. And then the algebraic way which we discussed earlier, which is looking at the delta as kind of this operation where we take the final volume that we have in the tub and we subtract the initial. So what's the final volume in the tub in terms of H?
The length times width times final height.
Yeah, length times width times final height. And then subtract length times width times initial height. And at that point, we've got a few things we can factor out that are the same in both terms, right? We could factor out length and width because those don't change. And we're left with H final minus H initial. And that gives us length times width times delta H, right? So the algebra, the geometry, they definitely agree, which is good. So let's say, because we're humans, right, we're less interested in a change in volume because we have a hard time eyeballing that. And we're more interested in the change in height. So what might I do next to isolate the change in height?
Divide by length and width.
Yeah. Divide by length and width. And so what I've found is that my change in height is equal to 1 over the cross-sectional area times my change in volume. And this really kind of intuitively makes some sense. Let's add something to it though. Let's say that we're interested in a certain time interval. And, based on our last graph, when we were just looking at volume increase as a function of time, we were able to graph it by using, delta V over delta T. That was the ratio of that right triangle that swept out that line. And so what could we do to both sides to get ourselves a delta V over delta T, a rate that we already know, assuming we know it from the faucet? I mean, this is a great formula if you're just asking, oh, I added 2 meters cubed. How much should my height rise by? But if I know a flow rate, delta V over delta T, 1 meter cubed per second, what could I do?
So just divide by delta T.
Yeah, that's all it is. I hope at some point today, Nick is going to get a little closer to his answer on our differentials, fractions, or ratios, right?
Yeah. Yeah, and right now it's getting flashbacks from our thermodynamics class where you went from just an energy thing to the dot derivative or time derivative, and you just have to go find all the other things that vary on time and add a dot to them.
Yeah,
If you
yeah,
miss a dot, then you're
in trouble.
messed up. Yeah.
So, why was I allowed to just pair the delta T with the delta V? Why didn't I have to do it with the 1 over length times width?
The algebra rules.
Yeah. It's
It's just they're being multiplied, so
it's kind of how multiplication works, right? It doesn't matter how you pair it, if you have 10 times 2 divided by 5, it's the same as 10 divide 5 times 2, the same as 10 times 2 divide 5. It doesn't really matter where you put that delta T. We're just putting it underneath the delta V because it's convenient, because we already know that. If we know the faucet, right? If we've figured out a way to calculate it. So now we know the rate at which the height changes in time. It's just 1 over this cross-sectional area times whatever the constant volumetric flow rate is. So if the faucet is kept on at a constant rate, then the height must also rise at a constant rate, right? This is something that, Nick, you already recognized. there's two factors here. We've got the 1 over a. What sets that factor? What component of reality gives us 1 over a? Kind of a weird question.
It's just like the actual geometry of whatever object
Thank
we're
you.
looking at.
Exactly. Just the geometry of the tub. And then what sets our delta V over delta T?
The flow rate of the faucet.
Yeah, just the faucet, right? So it's time dependent. Is the geometry time dependent? No.
Not in
Geometry,
this case anyway.
not time dependent. And is the faucet dependent on geometry? Once you have the assumed flow rate.
I feel like the geometry of the faucet won't change anything because once the flow rate is set, it's not going to change after that.
Exactly. So what we call this would be a decoupled difference equation, right? It's decoupled because we have two factors. We've got the geometry of the tub and we've got the flow rate of the faucet. And those two things are separate factors that go into delta H over delta T. So if I were to ask you to think of an example of a way to ensure that you gain more height in less time, what's one way that you could ensure that the water level rises faster?
Really small area.
Yeah. So if A goes down, then delta H over delta T goes up. The speed at which the water level increases is going to go up higher if you have this really thin tube. And then the other way, right, you could just increase the faucet, the amount the faucet's depositing. And that's going to lead to the speed of the water level rising being higher. So we call this kind of a relationship over here inversely proportional. And this kind of a relationship directly proportional. And yeah, we can picture it, right? We've got, we could have a tall tub, we could have a short, wide tub. And of course, the height is going to change at different rates. But assuming the same faucet, the volume is going to change at the exact same rate. So could you think of a situation now where the tub being filled is not decoupled in this nice way, where the geometry and the flow rate are more intertwined?
Balloon.
A balloon?
Yeah, if you're filling up like a water balloon,
Yeah,
it'll
you're filling a
change
water.
as you're
That's
filling
a
it.
phenomenal example. I hadn't thought of that one. But exactly right. Like with a water balloon, the volume of the balloon is changing because of the water you're putting in it. So that's a great example of a case where the geometry and the faucet are intertwined.
Maybe even just a normal balloon where you're blowing the air in and it's filling it up even bigger.
Exactly. Yeah, so there are cases where these things can be intertwined. And why it's important when they're intertwined or not is, I mean, let's think of just exactly what we can do here with this equation. So notice we have a difference equation. Do we actually have height as a function of time yet?
No, we have height as a function of volume, but that's it.
Yeah, right. So were you saying like up here, we could find height as a function of volume?
Yeah, or we also have that delta H equals 1 over LW on the
Right.
bottom.
So we have change in height as a function of change in volume. If we rearrange our volume as a function of height formula, we find that the height as a function of volume is just the volume divided by the cross section. So we've got those two things. Let's take a look at the difference equation and see if we can find h as a function of time using similar methods. So first thing I'm going to do is I'm going to take my delta h and separate it out, and my delta v and separate them out into differences. And what substitution did we do last time that turned this into a function versus an interval?
We put a variable in its place.
Exactly. So which thing should I replace with a variable?
H final,
Um,
right?
V final? What should I
Yeah,
put there instead?
just V.
Yeah, I'm going to write it as v as a function of t. And we keep the v initial. Over here, which of these should turn into a variable?
We're trying to find the height as a function of time. If we're trying to find the height as a function of time, then I think the H final should just become H of T.
Yeah, perfect. Then we could solve for h of t. And I'm going to write this as just 1 over area times volume as a function of time minus volume initial plus h initial. Does this look too complicated to anyone? Does this feel like it could be reduced at all?
I mean, we could probably make some other substitutions, like for HI.
Right. Yeah, maybe like because volume and height are like very tightly bound in the tub, right? Like if you know a volume that's in the tub, you automatically know a height, right? So we could come up here and we could say, well, H initial is nothing more than V initial divided by cross-sectional area. And then we could distribute the 1 over cross-sectional area. And what happens? Gone. Didn't matter. So as it turns out, for this nice decoupled case, where the geometry and the faucet rate are separate, h as a function of time is just volume as a function of time over cross-sectional area. And volume as a function of time, we assume we know what it is. You know, we said it was linear before, so some rate times some time. Does the volume formula here need to be linear for this whole thing to work? In other words, does this need to be constant pressure, constant flow rate?
I don't think we have anywhere that depends on that assumption.
Yeah. Nowhere did we make the assumption that V of t had to be linear. So this actually works for any volume as a function of time. And that's to do with the nice decoupled system and the fact that the geometry is so independent from the flow rate. Now, I would like to point out another thing about the differentials, which is interesting. Before, we had a graph of t to v. And once again, I'm going to go ahead and assume the initial value of v is 0. And what was the slope of the v to t graph? So when we're comparing velocity to time, what was the slope?
The flow rate.
Yeah, exactly. And that was just delta v over delta t, right? And then next up, what if we plotted, say, a height as a function of volume? The one that Nick found for us. Was that a linear graph?
Yes,
Uh,
but it had a negative slope. Or
This one
sorry,
up here,
a fractional slope.
a fractional slope, right? So this one has slope what? If we have h of v equals 1 over a times v, what would the slope be in this case?
1 over a.
1 over a, right? So h to v graph has a slope of 1 over a.
Yeah.
And then ultimately, we were really curious about what the h to t graph would look like. Because at the end of the day, like we're trying to build a water clock here, we need to relate height to time. What was the slope of h to t?
the delta H over delta T one that we had.
Right? I feel like I kind of erased that, but remember we divided
Yeah.
both sides by delta t, and so we had 1 over a times delta v over delta t. So,
Yeah.
I mean, I suppose in order to really see this, I mean, isn't delta h over delta t kind of the definition of the slope of the graph of h to t?
Mhm.
Right over here, we had delta v to delta t, and that was the slope of v to t. So I think it's safe to say that the slope of h to t is delta h over delta t, which we found an equivalent expression for. It was 1 over a cross-sectional area times delta v over delta t. Does anyone see a cool relationship popping out between those three graphs and their slopes? I suppose to make it clear, I could write over here that 1 over a is really delta h over delta v.
They're all linear for one.
They're all
And all
linear.
positive.
That's nice. That's helpful. But how do they relate to each other? Like, we related height to volume, volume to time, height to time. There's these kind of three relationships here.
The slope of height to time is the product of the first two.
That's right. The slope of height to time is the slope of height volume times the slope of volume to time.
Nick, there's your answer.
We're
Ah.
getting there. There is more subtlety, but right, like we're seeing here in this linear case, like, oh look, the delta v's cancel, right? So this is our first encounter with a rule of calculus, right? I'll just throw it out there. It's called the chain rule. And we really haven't even touched any like really desperate calculus yet. And here it's popping out of a linear example. But it's really important to note, right, that height is only a function of time because volume is a function of time, right? And in this case, how it really goes is time affects volume, volume affects height. This is kind of our flow chart of what's causing what. We say time's our parameter of change. It's parameterizing the change of volume. And then as volume increases, the height of the tank increases. So this is how it's related. When I said it was decoupled earlier, I meant that, well, time doesn't change this and height doesn't change that, right? Like we just have a nice straight line of cause and effect mathematically that goes through here. All right, so we've gotten just about everything we could want out of that model. Next, the question Nick so masterfully answered about a case where height and volume and time would be more inextricably intertwined with the water balloon is a little bit more complicated than I wanted to go today. So we'll stick with, although this is no simple case either, right? Now you're sitting in the bathtub and you're thinking about, I wonder how the height changes in time. What do you think? What's different?
You have a irregular shaped. Well, I guess you have a tub now with a human hole out of it that the water goes
Right.
into.
Like it was a nice rectangular basin, but then you had to go sit in it, right? And your body doesn't allow the water to just flow in. So I tried to draw some dashed lines here to help visualize, like, really, in this case, you would really need to define area as a function of height. And in order to do that, firstly, you'd have to sit perfectly still. And secondly, you'd need to, like, I don't know, come up with some way to measure your body's components, we'll call them. Um, so you're sitting in a rectangular basin, and now the cross-sectional area is no longer constant. This causes a stronger coupling between the tub geometry and the faucet's volumetric flow rate. Because the amount of accumulated fluid leads to a different cross-sectional area of the tub, we now have a cross-sectional area that's dependent on height. And remember, we're trying to solve height as a function of time. So if area is a function of height and height is a function of time, then area is also like an indirect function of time, right? So now where we used to have this nice time, volume, height, now the height is going to start affecting the volume. So you've got this extra kind of linkage and information that's going to make this really difficult. I recommend we don't try to solve this problem because, there's just a lot that goes into it. But I think it's a good example of like, this is when you need a little bit more. You can't just rely on the constant fill rate and the constant height rate. This is an example where those two things become very bound together.
That's when you approximate a human as a cylinder.
Exactly, right. The spherical cow. But the first example that I think is non-trivial, that where the cross-sectional area changes as a function of height, would be this triangular basin. So we're going to spend a little bit of time with this triangular sided basin. And it's still pretty nice geometrically. How do we find, well, we always try to kind of start with, can we find a volume function? Like volume is a function of something. I don't know. Does anybody have an idea of what that function would look like?
You can go with your normal like triangle things of volume is what length times like 1/2 length times width times height, or would it be? I don't know how it works with pyramids actually.
No, that
I think
works
it's
good, right? Because the length is the same for every height. The width
yeah.
is definitely changing now, so I use a lowercase variable there. So really what you're saying is like, oh, well, the area of this side rectangle would
Yeah.
be width times height, right? And then, well, I'm taking half of it because that's what a triangle is. A right triangle is half of a rectangle. So
Mm.
this would be like the side cross-sectional area and then times it by length, extruded out. That works good. So really what we have now is we have volume as a function of two variables, width and height. Is there any way to squeeze it down to maybe single variable?
Well, your width and height should be related in some way
And why do you say that?
because as your assuming this is like a perfect 45 like as your height increases your width increases by some fixed amount.
Right. So kind of, what we learned from the linear flow rate even is that it's pretty clear here that the relationship between height and width is a line, right? So how do we put that into an equation form? Let's say down here we have your origin is 0, 0 for, width and height. Or actually, let's say that's height and width or something like that. Um, and then up here, what would this point be on the line?
Like your capital H, capital W.
Yeah, capital H, capital W. So both of those are points on the line. So we should be able to figure out the slope of the line. The slope of the line would be equal to what?
Delta 8, no, delta W over delta H.
Yeah, that would be the symbolic way to represent it, right? And then because we know that delta W is just capital W minus 0, and delta H for this specific interval is big H minus 0, that we could replace the slope with just W over H. And then we also know that it passes through the origin, so there's no like initial value that we need to tack on here. It's just a straight shot. So width as a function of height is just width over height times H. And you can kind of double check this for yourself really quick, because what do you get if you plug in capital H for the variable H?
And you get the maximum width.
Exactly. So it lines up in that way. So when we substitute this in, now we just have volume as a function of height. Something interesting happens here, which is that we plug in this linear function for width in terms of height. And now we actually end up with 1/2 length times width over capital height H squared. So the volume as a function of height is no longer linear. It's quadratic. Now, one explanation for that, or one factor in it, is that increase H leads to increase V. Just, from the constant cross-section case, that was the truth, right? If H is going up, V is going up. And then the second component to that now is that increase H leads to increase of the cross-sectional area as well. Right, so let's take a look at that cross-sectional area function. It's now a function of height, like we were discussing. What would the area function of height be? If you consider, say, this is the cross-sectional area of some height.
You have your width as a function of H. So you can use I guess just multiply everything by H, I guess. Give you
Right.
area.
Yeah, it's just length times width, and then width as a function of height is just this. So we see that the area is a function of height that is a linear function, right? So our cross-sectional area is linearly increasing, but that actually leads to a quadratic volume, because one factor of H comes from just, well, height means more volume in general. And the other factor comes from, well, height increases cross-sectional area. So each slice higher you go can hold more volume as it is.
Can you get anything more than a cubic function for volume?
For volume, can you get anything? Absolutely. We will go only up to cubic today, hopefully. But like, I can keep cutting this side of the tank with weirder and weirder polynomials.
Okay.
And so like you're seeing ahead, but the next case we'll do is when the tank is cut with a quadratic.
Okay.
And that gets a little bit more complicated. But now that we have volume as a function of height, we can do a couple of things with it. One is we could find the algebraic difference, right? The change in volume. So I would apply that change operation to both sides. And on the left side, it's pretty cut and dry. We just have delta V. That's what we're trying to solve for. What happens on the right side?
You can kind of distribute your delta through almost.
Yeah. What do you mean by that, though?
Or yeah, I guess another way you could do it is just take the initial values minus the final values and then see
Yeah.
what cancels.
Right. And you're like, well, this 1/2 length times width over height, these are like absolute numbers. These are constants. And so really, and we showed this a little bit last time, but you can distribute that change operation because of the way it works, right? If you have 1/2 length width over height times h final squared minus 1/2 length width over height times h initial squared, all the constants can be factored out. And a way to kind of speed up the process is just to say, well, this difference operation, just like you can pull out any constants. And then what you're left with is just 1/2 absolute length, absolute width divide absolute height. And then, this isn't delta H. Right? This is important to note. Delta H squared is not the same as delta H squared. So in other words, H final squared minus H initial squared is not delta H squared. We've got something else going on there. Does anybody know a way of factoring this?
A difference of two squares.
Yeah, difference of squares. So what does it give us once we factor?
H final plus H initial quantity times the difference in the heights.
Right. Jonathan got us our delta H. We needed that, right? We need that to be a difference relation. So we've got delta V equals 1/2. Oh, and actually, I'm going to move the H final and H initial over here to be over the 2. Length times width over height times delta H. So this is our difference equation. It's pretty, I mean, it looks nice now. I'm assuming everybody's dealt with difference of squares in this group. So probably don't need to jump into why that particular factoring works. But at this point, I would say, okay, we have a delta V on this side. We have a delta H on this side. Great. That's what I wanted to relate, right? I wanted to say, if I change my volume this much, how much does my height change? Have we completely fleshed this out yet, though? Like, is it just a delta V over here and a delta H over here? Or is there a missing piece that we're not considering? Maybe a missing delta H.
The H final plus H initial. Is that what you're talking about?
Yeah, there's something in there, right? Because H final equals H initial plus delta H. And so that's another way to write it out. So if I were to substitute that in here, H final now equals H initial plus delta H. So we can take it further. Does anybody see how this is going to reduce?
You're gonna end up with
Well,
a
we have
delta H squared. Yeah.
Yeah, there's going to be a delta H squared, right? Those H initials add. So you get 2H initial over 2 length times width over height times delta H. And then over here, we have a 1/2 length times width over height times delta H squared. And those 2's cancel, so I can get rid of those. Length times width over height times height initial. So actually, in this case, if you want to know delta V, you have to calculate delta H and square it. There's not a nice way to isolate delta H here. You'd have to do like a quadratic formula or something. I don't want to do that. But before we go that far, it might be in our interest to try the geometric way.
So for
this is
this,
kind of, go ahead.
so for this way, we're saying to know the change in volume, or to know to know the change in volume, you must know which height you're starting at.
Yes, that is true, right? You have to know the height you're starting at because a change in V, like for example, up here, if like say you're starting down here when the tank's not full
Mhm.
and you fill it up to like there, right? And that's some amount delta V. And it's some height 1 that you pass through delta H1. If I fill up by that same volume, so the same delta V, have I increased by the same amount of height?
No,
Why
it'd be
not?
less because you're using more of your volume is bigger than
Cross-sectional
your,
area is getting bigger.
yeah,
So
your
for the
cross-sectional area.
same volume, delta H2 is going to be less than delta H1. And so that's why in this case, H initial actually shows up in the change formula, right? You need to know what that height initial is in order to figure out how the change in volume relates to the change in height. But when you look at the geometry, right, I've sectioned this off in a way where I'm saying the change in volume total is this V delta V0. That's if you were to set your cross-sectional area to constant and just pretend it's constant through delta H. That's delta V0. And then delta V1 is this triangular wedge. And if you calculate those out, let's see here. If you calculate out what those are just using geometry, you'll find that delta V0 is equal to, let's see here, length times width initial times delta H. So length times width initial times delta H gives us that kind of constant cross-section rectangular approximation. And then for the triangular wedge, over here we have a delta W, change in width. Here we have our change in height, and it's still the same length. So that volume is 1/2 length times delta W times delta H. And if you use the relationship we found that relates width to height, then width initial is width absolute over height absolute times height initial. And delta W is width absolute over height absolute times delta H. And so when you play this out, you end up, with the algebra agreeing with the geometry, which is always good. There's two ways to do it. In this case, it won't always be as easy to see the geometry. But just notice that the delta H squared term is that triangle. And the delta H term is this rectangular shape. And so at this point, we could say something like this is a linear increase in volume because it varies with delta H. But it's representative of setting your cross section to be constant and pretending it stays constant from your initial location. And then this over here is a quadratic increase in volume caused by a linearly increasing cross section. So why does this matter, though? Why does this matter? It seems like a lot of algebra, right? But the next part's the fun part. Let's see if I can get out of here and share another screen. All right. So when we plot the delta H function and the delta H squared function, right? I'm just plotting it as x and x squared. And let's see here. Where's 1? This screen looks awfully weird. I wonder why. You guys see that delta or that x squared and x agree at 1. Right? You plug in 1, they agree. If you go to values bigger than 1, delta H squared dominates. And delta H just kind of is slow and steady. But if you go to sub 1 values, so you go to really small values of delta H, just look at that. Look at how quickly the delta H squared hugs 0. And no matter how far you zoom in, the delta H, right, just the linear function, it starts completely dominating the squared function. So this is the motivation, right? Even without talking about making things infinitely small, right? Like even look, even at 0.1, even at 0.1, x squared is significantly smaller than x. You start getting down to 0.01 and even lower, 0.001. I can't even tell that the delta H squared line is off the 0, right? It is shrinking enormously quickly, okay? So the purpose of showing that is really to say that as delta H gets small, I'm not saying infinite decimals. I'm just saying small, like the practical definition that an engineer would use small to mean, right? Delta H is small. Really, in those cases, delta V basically becomes delta V0, right? This constant cross section does a great job if you do it over really small delta H's. Of course, if you do it over really big delta H's, then that triangular wedge starts getting massive, right? You'd imagine if you did an approximation down here and you tried to do that constant cross-section approximation here, that triangular wedge is a massive bit of volume, right? But if you do it over small delta H, only the linear term survives. The linear increase in volume. Everything the delta H squared is too small. Doesn't matter. And this pops out in a really interesting way up here. If we go back to where we stopped with the algebraic case, before we plugged in this H final equals H initial plus delta H, imagine if delta H is very, very small, how would H initial and H final relate to each other? We get that delta H just tiny. Change in height is minute.
They'd be almost the same value.
They'd be practically equal, right? So now I come up here to my delta V. And instead of H final, I'll plug in H initial. And this is where you start saying, thank God for that too. Right? Because H initial plus H initial is 2H initial. You divide out the 2, you just get H initial. You get length times width over height times H initial times delta H. That is delta V0, right? So what I'm saying is, even if we didn't know that a triangle was half of a square, we could have figured it out by squeezing delta H smaller and smaller and figuring out what that constant needed to be to cancel out and give back only the linear term. Now, at this point, we've got about 30 minutes left. There's a few directions I can go. I think I want to get to the quadratic tank, but I think we're going to spend the next session with these water tanks still because it's so rich. There's so much to learn about calculus here without even calling it calculus, right? We're just doing finite differences at this point.
Are we
Although
going to do
before
one
like I
that's,
need
go ahead.
I was going to ask, are we going to do one that's kind of like a hemisphere? I think that could be really interesting.
At some point, yes, there'll be something like that as well. But for now, I think what I'd like to say is we could dig deeper. I'm going to let you guys pick. Would you rather see what? Would you rather go in the direction of the rate of change of the rate of change, or would you rather go to the quadratic basin and touch some new dirt?
how long will rate of change take, do you think?
Probably 15 minutes.
I'd be kind of curious to see that.
Yeah,
I agree.
I thought it was super cool too. And the quadratic it's really cool as well. But I think before we move on, I at least need to say that as you squeeze delta H really, really small, right? I'm finally going to use the symbol, right? I'm going to squeeze delta H really close to 0. That we start, instead of using delta V, we start using dV. And instead of using delta H, we start using dH. And the real difference is, remember, as we said, as delta H got very small, H initial was pretty much H final, right? And at that point, why not just call it H, right? So as we squeeze delta H smaller, we go from differences to differentials. Differences have 2 points, right? A V final, a V initial. And they do the difference between the two. A differential is what happens when you squeeze those points so close together that for all practical purposes, it's the same point. And so we're going to start using these differentials in some cases. I think we should do rate of change of rate of change because I think it's really rich with the triangular basin case. So
one quick question with
yeah,
that
go
like
ahead.
dv and dh. Would it be correct to kind of say that assuming like dv and dh are in terms of t, that dv is equal to like delta v, or the limit of delta v as t approaches 0? Could you is that basically what the shorthand is saying?
Sure. Yeah, I suppose you could say that, right? I haven't put time into this yet, right?
Yeah.
So like in this case, we haven't even talked time or solving height as a function of time. But yes, height and volume can both be modeled as functions of time. So you could say
Oh,
over a really small time interval, and it will give the same result.
okay, but in this, we're not even saying that dv is in terms of anything right now. We're just saying like a very small change in v.
Exactly. And we've found the way that it
Okay.
relates to the very small change in h. And the interesting thing to note here is that by the time you get to dv, what used to be this finite difference thing where you really needed to account for the triangular wedge, right? As you get down to the differential scale, these terms disappear. Those higher order, delta h squared, delta h cubed, they fall off so rapidly. So by the time we write dv, it's really only the linear increase that matters. So it's only that constant cross section that really makes a difference. So at that point, we might say dv equals this whole stuff times just h, because who cares about initial and final? They're squeezed so close together. We'll just call them h now. And then delta h becomes a differential dh. And at this point, like you mentioned, Nick, we treat them like fractions a whole lot, right? Divide both sides by delta or dh. And what you end up with is what people call the derivative of volume with respect to height. Right? So as far as we can see, anytime it's appropriate to treat the finite differences as fractions, it's absolutely appropriate to treat their differentials as fractions or ratios as well. But we'll
Okay.
dive into this more as we get into multivariate stuff too, because there are some cases where it looks like they aren't ratios, but there's actually a deeper meaning to that than just that they're not ratios. I would say differentials are absolutely ratios, is my contention on that.